Hello, everyone. I'm Yong Hee from DuPont. Today, I'm going to talk about applications of NMR predictors in polymer research and complicated mixture studies. So first, I want to give a quick introduction to DuPont and also my organizations. And then I'll show you my evaluations of NMR predictors. And after that, I will give 3 quick examples of application using ACDLabs C13 NMR predictors. And after that, it's just my concluding remarks. So DuPont is a 223 years old company. Over the 2 centuries, its product portfolio have many dramatic change, and currently is focused on water purifications, personal protections, industrial technology, especially in the house and residence construction. And also it has some great products for automotives. So here I just show some feature brands that you might have heard about, like Kevlar, Nomex, Tyvek, and Great Stuff, and Film Tech. So I work in the core analytical science department, which does not belong to any single business. So we support all DuPont business, and we deliver innovations, value, and growth, and through analytical science-based solutions. So we not only support R&D, application development, but also manufacturing and customer, TS&D type of works. We just basically do, whatever is needed from us. So over my career, I found that the biggest NMR challenge is a complicated samples. It's normally a mixture of polymers and small molecules. It's quite common to have 10 components or more. And also to make it more challenge is most information we want is for the minor components. It can be percent level or even low. So we do have some tools, and one of the major tools we have been using is ACDLabs NMR predictors. I'm a loyal user to that for 18 years. I also advocate my colleagues to use that. And so when it comes to the NMR data interpretations from the spectrum to the structure, from my understandings, there are 3 possible ways. The first one is the traditional way. You need to run some 2D NMR and try to build the connections, through carbon-carbon, carbon-protons, and then hopefully, that you can get structures. The second way is taking advantage of the digitizations, also the advanced computing technologies. You can store all the data in a database and then run your spectrum versus the database to see if you can get some good match. And the third way is to do a predictions. Of course, it also needs a base, but it's based on a type of algorithms or theory, and then you do need a real data to feed into that and try to verify and or improve the predictions. So I have been using all 3 ways, but predominantly relies on the predictor. So it might be related to the specific type of work I'm doing. The first work is polymer studies. So polymers have too many structural variations. So because of that, the spectrum normally has a lot of peak splittings, broad peaks, and just make it a very crowded. And in the upper right corner, I just show a simple block copolymer. It's a binary copolymer, only have 2 monomers. And even for this simple polymer, you can have a block copolymer, have a random copolymer, an alternating copolymer, or just somewhere between. So basically, it's kind of a endless and structural variations. So that makes the data interpretations almost impossible to figure out entire polymers. So normally you can only focus on a local structure, and which is perfect for the NMR predictors. So the second type of work is a complicated mixture deformulations. So as I said, it could easily to have 10 components or more, and so there's a lot of peak overlaps, and which makes both the 2D AMR and also the data search is not easy. The third type of work is discovery molecule synthesis. So in this case, of course, it's a new molecules you are making. There's no existing data in the database. If you run a search, of course, you will not get a good match. So the next question is which AMR predictor to use. So over the past decades, both myself and my colleagues, we have run some comparisons because I always want to use the best tool. And we compare, both commercial and also there's some free predictors from academia. And if you go to any conference, you can easily see some people show a free predictors. So we have run some comparisons, and our conclusions is always the same, that ACDLabs gives a more accurate predictions than others tested by us. So here I just show one example. It's a random example. It's not specifically selected molecules. It's just by chance that's the one I'm working right now. So I run both a ACD predictions and also a MNOVA predictions. As you can see that for half of carbon on the table, and both predictors gives a quite accurate predictions. However, for the other half, the one values highlighted in red, you can see that ACDLabs gives much more accurate predictions. So that's the main reasons, I stick to ACDLabs for a long time. And of course, there's some other features of ACDLabs AMR predictors I like as well. So for example, for the predictions, each peak, it provides a confidence level. So that's a nice feature for you to judge how reliable is your predictions. So from my personal experience, so if the difference between the real data and the predicted spectrum is less than 2 ppm for a peak, so most likely you got the right structures. If the mismatch is between 2 and 5 ppm, then you might need some double check using another techniques, or propose alternative structure, or consider some solvent effect if the molecules could have a strong interactions with the solvents. And if the mismatch is larger than 5 ppm, so which normally means you got a wrong structure, you need to work again. Another feature is for the data that have been used to do the predictions and also the algorithm, you can select what database you can use. So this is especially important for samples that can have strong solvent interactions. In this case, you can just say, I only want to use a subset of the data that is using exactly the same solvent as my spectrum to do the predictions. So that's a really nice features to get a better predictions, especially when your sample can have a strong solvent interactions. And the last one is, for the database that's used in the predictions, it shows you the structure. So if you click on a certain carbon, it just shows you what structures and that carbon is. So it's a nice feature. Some people like, just like my colleague. Personally, I don't use that much, but it's up to you. So here is a quick screenshot of predictions for these molecules. And as you can see, for each peak, it shows you a confidence error bar. So that's a nice feature for you to judge how reliable is your structure. And also, if you click on any carbons on structure, it will show you a table, of what data is used and what solvent. Of course, as I said, you can narrow down to use only a subset of the data that using exactly the same solvent, or you can just use, the entire data set if the sample is not solvent sensitive. And again, as I said, it will show you what structure have been used in the database. So to me, it's really nice feature. And I also evaluate, carbon predictors, protons predictors, and also other nuclei predictors from other vendors. Here, just only comparing the carbon protons. So I personally prefer carbon predictor over proton, just because the carbon spectrum is much better separated the signals. You have more signals to use for predictions, and also the solvent effect is less pronounced for carbon, comparing to protons. And another reason is right now the crowd probe is quite common in a lot of labs. For example, in my lab, we have 3 crowd probes, so we can have a great data, the great quality data to use for predictions. I occasionally use the proton NMR predictors, but it's mainly used for a single component sample or a major component in mixtures. But I do use a lot to understand a spectrum rather than assign a structure. For example, I already know the structure of the samples. I just try to understand the proton spectrum, the peak splitting. In those cases, I can use NMR predictor spectrums to help me, quickly understand the spectrums. When you use the NMR predictors, you don't want to jump right into it. Before that, you have some preliminary work. The reason is the sample you work is most likely a mixture. So, and you have to separate the peaks first. So you have to separate the peaks to several groups. So each group, could be one single component or just one local structures. So in either case, you can use the NMR predictors to predict those and to see how good is the match. So with that, I just we give 3 quick examples. So the first one is for polymer studies. So for polymers, due to the short T2, some cross peaks might be missing in 2D NMR spectrum. Actually, is quite common. I have some samples, I know structures, I run the 2D NMR spectrum, I just cannot find the correlated peaks of the structures. So that's why, personally, I cannot completely rely on 2D NMR to interpret the spectrum of a polymer. Also, unlike small molecules, NMR database of polymer are very limited. Also, I'm not aware of a digital database for polymers. If anyone knows, I will be happy to learn. So in addition, it's impossible to draw the entire polymer structures. As I said before, there's unlimited variations. So because of that, you cannot rely on a database search to interpret a polymer spectrums. But the good news is, majority of the time, we only need a local structures in a polymer. For example, just one functional groups, N groups, a branching, a monomer sequence. So in this case, NMR predictor is perfect. So you can just predict that local structures. So here is a cysteine NMR spectrum of a polypropylene oxide. It's a pretty simple polymer. It only has 5 major peaks, and that's the backbone. And then we have 3 minor peaks. The minor peaks 2 and 3, based on my experience, and that's it seems like it's the end group of the polymers. So propylene oxide is an asymmetric monomer. So when you connect 2 monomers together, you have 2 ways to connect. So you can connect head to head or head to tail. So here I just draw the 2 different connections, and then I just run a predictions. Just only focus on at the end groups. So I do found 2 peaks that is very close to the predictions. Here you need to ignore other peaks because I didn't draw the entire polymer structures. So that's why all the other peaks is so scattered. So, but I do found 2 peaks that in end groups that is very close to the real spectrums. So also, of course, you need to combine some other independent informations, and I'm quite confident that it is the end group structures from those small signals. So with that, I can assign the peaks for every carbons of the polymer end groups. So the next examples is a complicated mixture deformulations. As I said, for this type of work, the key is to separate signals. And how to separate signal, that's beyond the scope of this talk. It could be another half an hour, 1 hour talk. But here just show the things I have done. So this is a cysteine NMR spectrums of a commercial curing agent. So it has 6 major components and a handful of minor components. So here I labeled all the major components with a number. I just separate them to different groups. So you probably notice I separate them to 9 groups. So you might ask, you only have 6 components. Why there's 9 group of signals? The reasons is, for some species, I can find all the carbons. I can confidently say, hey, I find all the carbons for that particular structure so that I can predict the entire molecules. But for other components, it could be complicated, peak overlap, so I can only identify some fragmented structures. So that's why I have more groups than the actual number of components. So for those fragmented structures, once you use the predictors to find out the fragmented structure, and then you try to do some piece puzzle, and hopefully that you can figure out something. Normally you need some help, other independent informations, or from another technology. So for the sake of time, I'm not going to show you the piece puzzle here. So here I just use the group 5 signal as examples. So since group 5 is probably the second strongest signals in the spectrum, so I can easily tell that I found all the peaks and belongs to these molecules. So it definitely has aromatic structures. It has 2 substitutions. One of them is likely a carboxylic acid, and the other, is kind of like a phenol structures. So, I have 3 functional groups, aromatic, carboxylic acid, and a phenol groups, and and then for these substitutions, you can have also positions, meta or para positions. So then this now is perfect. You can just quickly try those different substitutions and comparing the predictions to the real spectrums. So what I found is this also position substitutions gives the best match to the predicted spectrums. But still, there are 2 peaks that offer. I think one peak is off by 4 ppm, the other peak is off by about 3 ppm. So to be cautious, I still asked my colleagues to run the LC spec, and he found the same species. So with that, I think I'm confident to claim that this is one of the components in the mixture. So the last examples I show here is a discovery molecule synthesis. Is a reactions between a urea and the aldehyde. So for these structures, for people who have some organic chemistry background, and the structure B here is the known structure. If you just do a quick search of literature, and it's a urea structure. And here the R is the butyl groups. So the entire molecules is not that big. I think it's a dozen carbons. So, however, when I run the C16 AMR spectrum of the final product from these reactions, there's more peaks than we expected. So this is the actual spectrums. And if you counted the peaks, there's about 2,000 carbons because since there's some overlap, so I'm not 100% sure it's double, but it's quite close to double the amount of carbons. And also, if you look at the spectrum carefully, several carbons they shows as a pair. So for example, there are 2 carbonyl groups, and there are 2 oxygenated carbons around 60 ppm. Also the peaks 9 and 10, that's the end group of the butyl groups. So they all shows as a pair, and other peaks is hard to judge, but it already shows some indications that this final product might be just a dimer of the structure B I just shown you. And then the next question is how they can form the dimer. So in this is the time that we could use some organic chemistry background. And we know that the N-butyl group, that is very stable. And also this 6-member ring structure is kind of stable. So on each molecule of the B structure, it only have 3 carbons that is kind of active. So you only have 3 carbons from each molecules, and then to play around to see how they can connect together. So I try different ways of connections, and then for each way, I just run a predictions against the real spectrums, and this is the final one that I found has the best match to my experimental data. So the part of reason because this forms another 6-member ring. So that's another reason I propose this structure, because 6-member ring is always a more stable structure than a linear. So but I would say most carbons is within 2 ppm of the error bar, but those 2 peaks have a mismatch of 4 ppm. So to be cautious, I do run 2D AMR, HSBC, HMBC, and then try to double check, make sure that the connections all exist in the 2D spectrums. And the answer is yes. And also, since this is for A publications, I do need more evidence. So ask my colleagues run the LC mass spec, and the answer is yes. They also found the structure. So, and just for your curiosity, this is the final reaction route. And originally, we thought the product is B, but the actual product is E. So this is the reaction route in case somebody has interest. So with the help of NMR predictors, we figure out the final structures. So with that, this is my concluding remarks. So in my case, the ACDLabs NMR predictors is very helpful for the NMR spectrum interpretations, and it's especially appropriate for polymer studies, complicated mixture formulations, and also discovery research. And I do want to mention that there's no one single tool is a super power, so you do need some complementary techniques, especially mass spec, to provide some other informations or just double check. Also, some organic chemistry background is a plus, because when you use the predictor, you need to put some your input. You need to propose the structures. So that's why some organic chemistry background is very helpful. And the last is what's the benefit of using the ACDLabs NMR predictors? So I bet different people will have different feedbacks. So this is just mine. In my groups and my lab have been, we just dramatically reduced the need of 2D AMR. So we reduced that by more than 95%. We only run several 2D AMRs a year. And in a lot of cases, we just need one quantitative C16 AMR spectrum plus a depth 135. And that should be good enough for us to propose structures and then start the predictions and comparisons. And another thing I want to say that, as I said, you do need some human input in order for you to use the predictors. You need to propose a structure. So that will give you the opportunities to incorporate your own intelligence, your knowledge, your experience to the interpretations. So that you can focus on the entire project, not just simply the NMR data, because you need to understand the project, the directions itself. So that gives you the opportunities of some new findings, and also make you innovator. I do have several patents because of that. So I like to know more about the project, and so these predictors also help me. And also, as I said, the NMR predictors is very appropriate for local structure. You don't need to have a complete data set. Even if you only have several peaks, as long as you can propose a structure, you can just use the predictors, to predict that and then to see. And so that's an advantage. And the last but not least is, the predictors is useful for quick screening of ideas. So there will be group meetings, and people just quickly, pop new ideas. For example, this is the right structure, or that might be a component. So you can just quickly use the predictors and to predict those proposed structures, and can quickly narrow down the possibilities. So it's a nice feature. So with that, I think I'm done with the presentations, and thanks everyone for your attention.